Hello everyone, today we will talk about flood flow. So, the flood is the material that can flow and has no definite shape like liquids and gases. In this chapter, we will study the two properties of moving floods, which are number one, flow, number two, viscosity. The flow of liquids are classified into two types. Number one, the first type is called steady flow. and, and the second type is called turbulent flow. So now we will study the steady flow. So now we will study the steady flow and its properties. Hydrodynamics. What do we mean when we say the word hydrodynamic? It deals with floods in motion. Steady flow, the flow of a liquid with a small, the flow of the liquid when its velocity such that its layer slide over each other smoothly. As we can see here, when a liquid moves such that its adjacent layer slides smoothly with respect to each other, we describe this motion as a laminar flow or a streamlined steady flow, where every small amount of liquid follow a continuous path called streamlines. Streamlines, its definition, the basis of different particles of the liquid during its flow in a tube. As we can see here, there is a streamlines here and there is a cross section, and these streamlines are moving through the liquid with V1, velocity V1 and velocity V2 and velocity V3. Okay, we want to know now the characteristics of streamlines. Number one, they are imaginary lines that don't intersect. Number two, the number of streamlines at any cross section of the tube is constant. Number three, the tangent at any point along the streamlines determines the direction of velocity of each particle of the liquid at that point. Number four, streamlines cram up at points of high velocity. Its density increases and keep apart at points of low velocity, and its density decreases because the velocity of liquid flow at a point is determined by the number of streamlines that pass normally by unit area at that point. Density of streamlines at that point. So the speed of flood flow increases by increasing the density of streamlines at that point, and decreases by decreasing the density of streamlines. These are the characteristics. Now, these are the characteristics of streamlines. After talking about the characteristics of streamlines, we should define the density of streamlines at a point. The number of streamlines crossing on unit area around that point. Okay, the properties of the streamlines. Number one, virtual lines don't intersect. Number two, tangent at any point along the streamlines determines the direction of the instantaneous velocity at that point. Number three, the density of streamlines express the velocity of the liquid at that point. Number four, they become near at points of high velocity and keep apart at points of low velocity. The conditions of steady flow. There are some conditions that we must or we have to do it for the steady flood. Number one, the liquid fills the tube completely. Number two, the quantity of liquid entering the tube at one end is equal to the quantity of liquid emerging from the other end in the same time. The rate of flow of liquid is constant along its path. Number 3, the velocity of the liquid at each point is independent of time, doesn't change with time. Number 4, the flow of irrotational. The flow is irrotational, no vertex motion. If there is no force of friction exists between the layers of the liquid, the flow is not viscous. If there is force of friction, it is viscous. Okay, now we want to know the volume rate of flow. We have some equation we must express with it to know the volume rate of flow. Number 1, the volume rate of flow, its volume, we must know that the flow rate. The flow rate is the quantity of liquids that flow through a definite cross-sectional area of a tube in 1 second is known as flow rate, and it can be expressed as number 1, the volume flow rate. The volume of the liquids that flows steadily, it's defined as the volume of liquids that flows steadily through a definite cross-sectional area of a tube in 1 second, and it is measured in cubic meter over second. Okay? The volume rate of flow equals the cross-sectional area times the distance covered by the liquid in 1 second, and it equals the cross-sectional area times the velocity of the liquid. QV equals A times V, and the volume of the liquid flowing in time t, volume QV times T equal A times V times T. The mass rate of flow. Now we must know the mass rate of flow after knowing the flow rate and volume rate. Mass flow rate is defined as the mass of liquid that flows steadily through a definite cross-section area of a tube in 1 second, and it's measured in kilogram over second. Now we want to know some equations, or from the definition of mass, we must know that calculating the flow rate at any cross-section area by assuming a quantity of liquid of density ρ and volume V and mass m flowing at velocity v for a distance delta x in time delta t through the cross-section area of the tube. Note that the density is the mass of a unit volume of the material. Rho equals m over volume. The density is measured in kilogram over cubic meter, and the density of any material is constant in a fixed temperature, so it's considered characteristic property for the material. Now, from the definition of mass flow rate, we must know that Qm equals m over T. The mass rate of flow equals the volume of the liquid flowing in unit time times liquid density. The volume equals the volume rate of flow times the liquid density. The mass of liquid flowing in time t, m equals qm times t equals qv times rho times t equals av rho t. Now, from the previous equations, we can conclude that the fluid flows steadily. The amount of liquid entering the tube equals the emerging out from it in the same time interval according to the law of conservation of mass. The flow rate, volume or mass is constant at any cross-sectional area inside the tube. Now we want to know the deduction of continuity equation, which means the relation between the flow speed of liquid and the cross-sectional area of the tube. Imagine a tube carrying a flood that flows steadily. Okay, it flows steadily, and we have A1, A2, the cross-sectional A2, B at the point B, and this have velocity V1 and this have velocity V2. The cross-sectional areas of the two planes are A1 and A2. The velocity of the liquid at the two planes is V1 and V2. Here we have V1 and here we have V2. The mass rate of flow of the liquid through A1, okay, we can call it Qm, equals QV times rho, equals A1 times V1 equals times rho. The mass rate of flow of liquid through A2 equals QV times rho equals A2 times V2 times rho. As the rate of flow of the liquid along its path is constant in the steady flow, A1 times V1 times rho equals A2 times V2 times rho. So A1 times V1 equals A2 times V2, and this is the continuity equation. So we have V1 over V2 equals A2 over A1. We must know something here. From the previous, we can conclude that the speed of a liquid which is flowing steadily in a tube at any point is inversely proportional to the cross-section area of the tube, or square the radius of the tube at any point. And we must know something also. The tube is branched into a number of branches if the tube is branched into a number of branches of different cross-sectional area. If the tube is branched into a number of branches of different cross-sectional areas, A1 V1 equals A2 V2 plus A3 V3 plus A4 V4. If the tube is branched into a number of branches in the same cross-sectional area, we can add here n, only n, AV, AV1, A1 V1 equals n A2 V2. Now here we can watch this video about floods kinematics or streamlines.
ME331 Introductory Course in Fluid Mechanics. Today we're going to be talking about some quantities related to the kinematics of fluids, or how they move, namely streamlines. This is followed by part 2 and 3 on streak lines and path lines. So let's get started in. I want to show you a little animation which is shown here. This is a numerical simulation that's running on my iPad, solving the equations of motion for a fluid for flowing around a cylinder. This is a very common prototypical flow. We have a uniform upstream conditions on the left-hand side, and the fluid's moving from left to right. The cylinder is making it move around it, it speeds up, and then downstream we see a very unsteady wake. What we're plotting in here, we see these small little colored line segments. These are velocity vectors, the color indicating the velocity magnitude and the orientation of the segment showing the direction that the flow is going. As we talked about earlier, this is a Lagrangian velocity field. And then we're also showing on top of that some smoke lines that are being released upstream off the left-hand side. And every once in a while a thick blob of smoke comes in to sort of give us a time reference point. Now the question is, are these what we're looking at, do these represent the streamlines of the flow? And that's what we'll try and answer here at the end of the problem, and also talk about some of the ramifications. Streamlines are actually the most important of these three lines that we're talking about, but some of the other quantities are easier to generate. Alright, so a definition for a streamline is simply a curve which is everywhere tangent to the local instantaneous velocity field. Okay, so now these are some very important keywords here. It's a curve everywhere tangent to the instantaneous velocity field. So what that implies is we're talking about at one instant in time. And these curves can look different at different instants in times if we happen to have an unsteady flow, as what we'll see here in just a second. So this represents the direction of the flow at any given instant, and that's why they're such a useful quantity to have a look at. Now let's talk about how to calculate this analytically. Here I'm going to show schematically just an arbitrary velocity field. This may be a stagnating flow here, velocity coming down from the top and hitting a plane and moving off to the right, as we see here. And these vectors are showing us the velocity at different points in the flow field. Now we're going to want to draw a streamline here at a fixed instant in time. And so at that instant of time, let's call it t, it's going to pass through a point of our choosing that we're going to call x0 and y0. And so let's say that that's this location right here, x0 and y0. And I've drawn the velocity vector that's shown here now. I've highlighted in blue. It has two velocity components in the horizontal and vertical direction. And if we zoom in on that, we're going to take the horizontal component to be u and the vertical component to be v. And we see that the curve that we want to draw has...
You know what can be kind of peculiar and surprising? The fact that whenever you want to shoot outside, everyone decides to mow their lawn. You know what else can be kind of peculiar and surprising? Water. And in the right circumstances, I could even take water that's flowing down and spurt it straight up. How? All of these things are possible thanks to the study of the flow of fluids, known as fluid dynamics. By now, you've picked up on the fact that even though we live in the physical universe, describing the rules of the universe sometimes requires us to pretend that certain things aren't happening. Like the time we rolled a bunch of stuff down a ramp and pretended that there was no kinetic friction. The same is true when we talk about fluids, because fluids in motion are dynamic, and there are many things going on in and around them all at once. So in order to grasp the essentials of fluid dynamics, let's just do some pretending, shall we? For one thing, we're going to consider the fluids in our examples to be incompressible, meaning that their densities won't change. We're also going to assume that fluids flow perfectly smoothly and have no viscosity. You've probably heard of viscosity before. When a fluid flows easily, like water, we say that it has low viscosity. Fluids that don't flow as easily, like honey, have a higher viscosity. And much like kinetic friction does in moving objects, viscosity tends to complicate things in moving fluids, which is why we're going to generally pretend that the fluids we're studying don't have any. Now say you have some water which exists under all of these hypothetical conditions in a pipe moving along smoothly. This pipe narrows about halfway through so that one end is more narrow than the other. This shape is going to affect some of the properties of the water's flow as it passes through the more narrow side of the pipe compared to the wider side. But one thing that won't change is the mass of water that's moving through any given area of the pipe over time. This is called the mass flow rate, and it's always going to be the same everywhere in the pipe. That's just because as the water flows through the pipe, it pushes along the water in the rest of the pipe too. So if one part of the pipe has, say, a kilogram of water moving through it every second, the rest of the pipe also has to have a kilogram of water moving through it every second. This fact that the mass flow rate at one point of the pipe will be equal to the mass flow rate at any other point is called the equation of continuity. And it can tell you a lot about the relationship between the velocity of a fluid and the cross-sectional area of the pipe that it's flowing through. Let's say you're an engineer for the water department of a hypothetical city, and you need to understand the mass flow rate of hypothetical water that's going through a certain point in your underground pipe system. But you don't know the mass that's going through that part of the pipe at any given moment. All you do know are the water's velocity and the area of the cross-section of that certain section of pipe. In order to describe the mass flow rate, you'll have to use what we know about density, area, and velocity to work out some algebra magic. First, let's have a look at the cross-section of that point of the pipe. From our last lesson, you know that the mass of the fluid moving past this cross-sectional area over time is equal to its density times its volume. And the volume of the fluid moving past this point is simply the area of the pipe at this cross-section times the distance the fluid moves. And from our episodes on the physics of motion, you will also know that the distance the fluid moves divided by the change in time is equal to the fluid's velocity. So by putting that all together, you can get a different version of the equation of continuity. At any given point in the pipe, the density of the fluid flowing through it times the area of the pipe times the fluid's velocity will be the same as for any other point in the pipe. And since you're dealing with an incompressible fluid, the density is going to be the same for every point in the pipe anyway. So really, you've just figured out that at any point in the pipe, the area of the pipe times the fluid's velocity will be the same as for any other point. It's the same thing we said before. The mass flow rate is the same for every point in the pipe, but instead of putting that relationship in terms of mass and time, you're putting it in terms of area and velocity. And in your role as a water department engineer, this is important for you to know, because it means that where the pipe is narrower, the fluid will have to flow faster in order to compensate. But here's the weird thing. A fluid that's flowing really fast actually has less pressure than when it's flowing more slowly. Sure, it might feel like it's exerting more force than when it flows through a wider opening, but that's not what physicists mean when they talk about the pressure in a pipe. They're really talking about the pressure on the walls of the pipe. This means that the slower the fluid flows, the more pressure it puts on the pipe itself. This is known as Bernoulli's principle. It states that the higher a fluid's velocity is through a pipe, the lower the pressure on the pipe's walls and vice versa. Bernoulli also came up with what we now know as Bernoulli's equation. It might look kind of intimidating at first, but when you break it down, it's actually just a way of combining a bunch of things that you've already learned. Bernoulli based his equation on the concept of the conservation of energy. As a fluid flows through a pipe, it won't gain or lose energy. This means that no matter where the fluid is in the pipe, if you take all the forms of energy that the fluid has at that point and add them up, they'll equal the same number as any other point in the pipe. To better understand this, have a look at how the three forms of energy in a fluid are represented in Bernoulli's equation. First, there's pressure times volume. In our episode on work and energy, we defined energy as the ability to do work. And when a fluid applies pressure and moves the volume of fluid that's downstream, it's doing work. So pressure times volume must be a form of energy. The first term in Bernoulli's equation takes that energy and divides it by volume, which just leaves pressure. Next, a flowing fluid also has kinetic energy. When we first talked about kinetic energy, we said that it's equal to half of an object's mass times its velocity squared. Again, Bernoulli divided this form of energy by volume to get half the fluid's density times its velocity squared. That's called the kinetic energy density, and it's the second term of Bernoulli's equation. Finally, a flowing fluid also has the potential energy that comes from gravity. And we said before that the potential energy from gravity is equal to an object's mass times small g times its height. When Bernoulli divided that by volume, he got density times small g times height, the potential energy density, and the third term of his equation. Why divide all these terms by volume? Well, when it comes to fluids, it's just easier to talk about things in terms of density than it is to talk about mass. So when you look at his equation piece by piece, you can see that Bernoulli was really just putting conservation of energy into a special form that would be useful for fluids. Now let's look at a special case of Bernoulli's equation known as Torricelli's theorem. Torricelli's theorem uses conservation of energy to find the velocity of fluid flowing from a small spout in a container. And it says...
So now here, after watching this video, we have to solve an example. In the opposite figure, shows a water container of volume V, which is being filled by two water tapes, tape X and tape Y. Tapes X and Y, such that if only tape X is used, the container takes 15 minutes. If X is used, the container needs 15 minutes to be filled. And if only tape Y is used, the container takes 30 minutes to be filled, and also in the tape Y, the container needs 30 minutes to be filled. What are the time required to fill the container by using the two tapes together? Now we want to fill this container with the two tapes together, and we want to know the time required. Now the solution of solving the givens are Tx, the time to be filled for the container to be filled by the tape X is 15 minutes, and the time to be filled by the container Y is 30 minutes. So QV equals QVX plus QVY. So the volume over T for the QV equals volume over Tx plus volume over Ty. So the volume of the container is fixed, and it is fixed, not change it. So 1 over T equals 1 over Tx plus 1 over Ty equals 1 over 15 plus 1 over 13 equals 1 over 10. So the time equals 10 minutes.